How's it going, everyone? It's Chow here, and today we are going to talk a little bit about hemoglobin, so let's get started. Okay, so hemoglobin, which is sometimes shortened as just HB, is a protein in our red blood cells that carry oxygen. I think that's pretty straightforward. What's probably more fascinating about hemoglobin, aside from the fact that it carries oxygen, is that it's actually a quaternary structure. So if you think back to the discussion on proteins, basically we have primary, secondary, tertiary, and quaternary structure. So what that means is that it actually has 4 separate subunits, with each subunit having a heme group, hence the name hemoglobin. And then each heme group is able to bind one O2 molecule. So it can in total bind 4 O2 molecules per hemoglobin. So you can see over here we have 1, 2, 3, 4 different subunits, and each subunit can bind an oxygen. So therefore, in total, a single hemoglobin can bind basically 4 different O2 molecules. What's really more fascinating, though, perhaps from a biomedical perspective, is that we have carbon monoxide. So carbon monoxide actually binds preferentially over oxygen, which means that if you have a high concentration of carbon monoxide in the surroundings, it's going to bind more favorably and more readily than O2, and this can ultimately cause carbon monoxide poisoning, and that carbon monoxide is going to starve the tissues of oxygen. Hence the reason why CO is so dangerous to us as breathing humans. There we go. That's a weird description. Okay. The next thing we have to talk about is this binding curve over here. So hemoglobin is fascinating because it shows positive cooperativity. So what positive cooperativity is that at low partial pressure of oxygen, so this is partial pressure of oxygen, one O2 molecule binds to hemoglobin. And what this causes is a change in the protein shape, which increases the affinity for other O2 molecules to bind. So what you can think about is, initially, hemoglobin is kind of reluctant to bind oxygen. But once it binds one, there's going to be a positive cooperativity that causes it to bind other oxygen molecules more readily after it binds the first one. So that's pretty straightforward. Now, in the lungs, the partial pressure of oxygen is going to be really high. So hemoglobin in the lungs is actually going to be 100% saturated, which kind of makes sense. You want to saturate your hemoglobin in the lungs because that's where you get oxygen. So then the hemoglobin is going to travel to tissues, and in tissues where the partial pressure of oxygen is going to be lower than, say, the lungs, one oxygen typically is going to be released from the hemoglobin to supply those tissues with oxygen. In extremely oxygen-starved tissues, the O2 reserves sometimes will allow for easier dissociation. So we're going to increase the dissociation of oxygen from hemoglobin because partially of that lower partial pressure of oxygen. So in oxygen-starved tissues, you can think about hemoglobin being more readily to actually release its oxygen that's bound to it. Now, in terms of oxygen-starved tissues, that's great and all, but there are actually kind of other factors that can cause this particular curve over here, which is in a sigmoidal shape, which means that it shows cooperativity. This curve over here for hemoglobin can actually shift to the right or shift to the left, depending on environmental conditions. So we can look at some of these conditions. Firstly, high altitude. So if you're at the top of Mount Everest, there's going to be really low partial pressure of oxygen. So the total amount of oxygen gas available in the surrounding per unit volume is going to be decreased. What this means is that the hemoglobin binding curve can actually shift left. So this curve can actually shift to the left, which is maybe more like this. And by shifting left, we're more readily going to bind oxygen. So we're going to bind oxygen more readily, we're going to bind it more efficiently, and not lose it as easily. Now, when you have high concentrations of carbon dioxide, so high CO2 concentrations, or potentially high temperature, this can actually cause the curve to shift right. So it's going to shift from this normal-ish position to the right. So it's going to look like this. And by shifting right, your body is going to kind of adjust to those surroundings and release oxygen more readily with that high CO2 concentration or potentially high temperature. In addition, when you have a low pH, so you have increased acidity, maybe perhaps indirectly from carbon dioxide, that's going to cause the curve to shift right. So if you have maybe a decrease in the pH, you're going to actually shift the curve slightly to the right as well. And obviously, if you actually increase the pH, so we're decreasing the pH over here, low pH, that's going to shift to the right. If you have a high pH, right, that might actually cause the curve to shift slightly to the left. So it's a sigmoidal curve. It shows positive cooperativity, but depending on what's around in the surroundings, it can cause the curve to shift slightly. And that's just a way that your body kind of mediates the necessity to pass oxygen to the needed tissues. So we talked a little bit about oxygen, but what about carbon dioxide? So in our body, about 5% of the CO2 is actually going to be transported directly as gas in the plasma. But about 20% of that CO2 is basically carried by the hemoglobin, and the rest is going to be carried as bicarbonate ions. So a lot of that CO2 within your blood is actually going to be carried as bicarbonate ions rather than directly as CO2. And we use this enzyme called carbonic anhydrase to help with the process. So carbonic anhydrase is over here, and it's going to rapidly convert CO2 and water into carbonic acid. That carbonic acid is going to dissociate into a hydrogen ion and bicarbonate, also known as bicarb. And these bicarbonate ions then enter into the plasma in exchange for a chloride ion. So that's going to be shown over here. So again, in tissues, acid and CO2 is going to be produced as we're respiring. So through tissue cellular respiration, we're going to be producing some CO2. That CO2 is going to ultimately lower the pH. As the pH lowers, the hemoglobin is going to bind less tightly to O2, so more O2 is going to be released, which is what we just discussed over here. So this decrease in the pH and an increase in oxygen release is called the Bohr effect. Now you have that high concentration of CO2. What is it going to do? What is your body going to actually do to that CO2? Well, you have to get rid of it. So again, what happens is your body is going to try to mediate this effect by converting that carbon dioxide into carbonic acid. So that carbonic acid is going to then basically dissociate into bicarbonate and hydrogen ions. So this process, again, is mediated by carbonic anhydrase. And then eventually this bicarbonate molecule is going to actually get out of the red blood cell in exchange for a chloride ion. So the conversion of CO2 into bicarbonate basically helps maintain the partial pressure of CO2, which can potentially allow and promote the movement of carbon dioxide out of the tissues. Now, once we get to the lungs or the alveoli, the opposite actually happens. So this process of conversion is going to be released. What we see is bicarbonate actually re-entering the red blood cell. And then after it re-enters into the red blood cell, it's actually going to be converted back into CO2. This CO2 is going to then be exiting the red blood cell and entering into the alveolus or the alveoli, where it can be basically exhaled and gotten rid of. So it's going to be diffusing down its concentration gradient into the alveoli, which is what's happening over here. So this is just a kind of a quick summary where in the respiring tissues, we're basically taking that CO2 that's created as a byproduct and we're getting into the red blood cell and converting it into bicarbonate. In the lungs, the opposite happens, and that bicarbonate is going to be taken up, converted back into CO2, and ultimately released into the alveolus, and that's going to be exhaled from the lungs. So ultimately what we're looking at here is this mediation by hemoglobin in addition to other components like carbonic anhydrase. So that's basically it for hemoglobin. I don't want to talk too much about the specific details. If you're interested in that, or if you're required to, read the book, show up to your lecture, go annoy your tutors, and we should be good from there. So I hope you all found this mildly useful, and as always, best of luck studying, and I will see you all in the next video.